In this video, we're going to talk about what makes atoms stable and consequently what makes atoms unstable. So if we look at what we're eventually getting at, I suppose I should say, is called radioactivity. So if we look at something like a hydrogen atom, right? We've got a proton, which is positively charged, as a nucleus, and then if it's not ionized, I've got an electron out here, in an orbital or an energy shell. I'm drawing it as an orbit in sort of the older model of the atom called the Bohr model, but we know that to orbit like a planet orbits the sun is not exactly what's happening here, but it's a useful way to think about it. So we'll go with it for now. But hydrogen has one proton and one electron. Now, of course, there are versions of hydrogen which also have neutrons in the nucleus, but if you were to go out in the universe and just find a random atom of hydrogen, the chances are overwhelming that it would be this type of hydrogen with one proton and one electron just whizzing around the nucleus. That's all well and good. Now, if we go up one element in the periodic table, in other words, if we go to an element with two protons, we don't find this. If this would be the nucleus, if we're talking about helium. Helium has two protons. If we just had two protons sitting next to each other, and when I say next to each other, I mean very, very, very close to each other. Atomic distances, the distances in the nuclei of atoms, are tiny. And remember, these are charges, and they have a Coulomb repulsion. Remember that the Coulomb force goes as 1 over r squared, so the closer you get these things, the higher the force. So even though these are pretty small charges, the Coulomb repulsion can be quite significant if they're close enough. So if we have an atom of helium with two protons in a nucleus, the logical thing to ask ourselves is, why don't these things fly apart? Why do they stay in the nucleus? The answer has to be that there is another force which is stronger than the Coulomb repulsion, which is holding these together. We know there's Coulomb repulsion, so if they're not flying apart, there has to be another force. What is that other force and where does it come from? Well, the answer is found in that this is not a complete helium nucleus. Usually, I will find two neutrons. Now, a neutron is so named because it is electrically neutral. It does not carry a charge. So I have two charged particles, which do not want to be near each other. And then I've got two neutrons, which don't really care because they're not electrically charged. So what we know about this force that has to hold this nucleus together is that it's stronger than the Coulomb force. For that reason, and because physicists are remarkably imaginative, we call it the strong force. Really, we call it the strong nuclear force because it's strong and it exists in the nucleus. So why don't these things fly apart, and specifically, why do we find neutrons here and ordinarily we don't find a neutron here? Well, the answer is because that the strong force actually arises from all these particles, which we call nucleons. If they're in the nucleus, we call them a nucleon. So the strong force arises from the protons, but it also arises from the neutrons. Just like gravity arises from mass and Coulomb forces arise from charged particles, the strong force arises from the nucleons, the protons and the neutrons. So the role of the neutrons now is to provide a strong force, at least a component of the strong force, while not contributing to the Coulomb repulsion, right? That's why we typically don't find them in the hydrogen atom. They're not needed. There is no chance that this is going to fly apart. It's just one proton. But here, if I did not have the neutrons, the strong force between the protons wouldn't be strong enough to overcome the Coulomb repulsion. So I add two neutrons and bolster up the strong force so that it is able to overcome the Coulomb repulsion. So if I move on to the periodic table and I go to lithium, There will be some forms of lithium where I find 3 neutrons. I should mention, of course, that isotopes are a possibility. An isotope, if you recall from chemistry or the readings in this class, is two different atoms of the same element but with differing neutrons. And so for hydrogen, I can have one neutron or two neutrons. For lithium, I can have 4 neutrons, 3 neutrons. So it kind of depends on which form you find. But in general, the number of neutrons goes up with the number of protons. If I go down to, let's say, oxygen, right, I will find 1, 2, 3, 4, 5, 6, 7, 8. So the ones you might not be able to see the the pluses, but the ones with something inside it are supposed to represent protons, and the others are neutrons. Now, please understand, I'm not actually making an attempt to show you subatomic structure here. I'm just putting in circles and drawing charges in them. That's not the point of this discussion. The point of this discussion is to show you that a couple things. As the number of protons increases, so does the number of neutrons. However, we can understand a few things about the strong force. The strong force acts over very short distances. So as long as I'm dealing with distances like I would find in a helium nucleus, the distance between these two protons, it goes to their repulsion, but the distance between all of these goes to their attraction. As long as I'm dealing with these small distances, the neutrons are able to bolster up the strong force just fine. But notice what's happening as I'm going up the periodic table, or down, depending on how you look at it. As I'm going up in number of protons, the atomic number, my atom is just getting bigger. And so what happens as the radius of the atom increases, or the radius of the nucleus increases, the strong force starts becoming more and more ineffective. And so as my atom gets bigger, the Coulomb force starts gaining traction, and the strong force is still able to overcome it, but with less and less certainty that it will do so. So at some point down the periodic table, beginning about with chlorine, which is atomic number 17, you start to find more neutrons than protons. And again, we're talking on the average here. You can find different isotopes of these things. But as you move into heavier elements, you start to find more protons than you do neutrons. So by the time you get down to something like lead, which has 82 protons, and it has, on the average, 207 nucleons, which is a difference of 43. You would have on the average, 43 more neutrons than you do protons. The reason for that is because if we're becoming more and more unstable, right, if this Coulomb repulsion is starting to win, the solution, or at least one possible solution, would be to just put in more neutrons. What does that do for you? It increases the strong force while not increasing the Coulomb force. So if you add another proton and another neutron, and all of a sudden you have the Coulomb repulsion able to rip the atom apart, maybe you add one more neutron and you stabilize it that way. So of course, when you add more neutrons, you're still increasing the size of the atom. And so you're starting to get into a 3 steps forward, 2 steps back situation where you are able to overcome the Coulomb repulsion, but the returns are diminishing because your atom is still getting bigger, and that in turn weakens the effect of the strong force. It doesn't weaken the strong force, but it weakens the overall effect of it. So at some point, you reach an atomic size which is going to be unstable no matter what. When this thing is big enough, the strong force is always going to win, ultimately, over the Coulomb force. As the atom goes into different states and different energy levels, you will find arrangements where the strong force is then able to make the atom, the nucleus, decay. And that Another sheet of paper. Nuclear decay is what we call, is what is termed, I should say, radioactivity. Something is radioactive if it is undergoing atomic or nuclear decay. It's a little bit of a misnomer. At some point in the late 1800s, early 1900s, when this stuff was being studied, people figured out that certain elements like plutonium and uranium produced different stuff. That's the best thing I can say about it. Right now is just stuff. Now, and they wanted to know what this stuff was, and so they figured out that if they put this this sample of radioactive material, uranium, plutonium, whatever you have, next to a magnetic field, right? So we have a magnetic field here, and the different stuff that this sample was producing was able to pass through the magnetic field. What they found was that some of the stuff was deflected that way, some of the stuff was deflected that way, and some of the stuff wasn't deflected at all. Of course, we know from previous work in this class, if you have stuff that is deflected by a magnetic field, that has to be a charged particle, right? So as I've drawn it, this is a little bit unclear, but the point is that some stuff was deflected one way, some stuff was deflected the other way. Like as I've drawn it, that's the right-hand rule is not going to work out too well here. But again, I'm not trying to actually show you which particle is deflecting which way. I'm just showing you that some stuff was deflected, some stuff was not. Let's deal with the stuff that was not first. This was termed gamma radiation. And it turns out that this is the only type of radiation here that is true radiation. When you say the word radiation, literally what that means is some sort of electromagnetic wave activity. So we're stuck with the word radiation for all of this for historical reasons, but this actually is the only one that's true radiation. This is electromagnetic radiation. It does not consist of charged particles, is not deflected by a magnetic field. What we're going to concern ourselves with mostly in this lecture are the two deflections. One, of course, would be negative and the other would be positive because they're deflecting different ways. They termed the positive alpha radiation. We can call it alpha particles because we understand that if it's deflected by a magnetic field, that means it's a charged particle. This was called beta radiation. We can call it a beta particle. All right, so what are these alpha, beta, gamma, which I should point out are the first three letters in Greek. This is like naming them radiation A, radiation B, radiation C. What are these things? Well, we're not going to really deal with the gamma radiation here, but we will talk about alpha particles and beta particles. We're going to do that in the next video.